Okay, let's unpack this. We're diving into something really significant today. The scientist Linus Pauling once said, "The greatest obstacle to discovery is not the scarcity of new ideas, but the abundance of old ones."
That feels very relevant here. We're looking at old ideas about the Amazon meeting some, well, stark new realities from a long-term experiment.
Exactly. This deep dive is all about a groundbreaking project, nearly 25 years old now, simulating future drought in the Amazon rainforest.
And it's not just abstract science. This is about understanding one of the planet's biggest carbon stores and how it might cope with what's coming. It directly impacts our climate future.
It really does. We're drawing heavily today from some excellent reporting in The Independent, which detailed this whole effort.
And our goal really is to figure out what these 24 years of simulated drought tell us. What have we learned about the Amazon's breaking points, its resilience, and importantly, what does it mean for you?
Right. Whether you're following this for studies, maybe competitive exams like the UPSC, where environmental issues are key, or you just want to understand the planet better, this is vital information.
It's core current affairs, really.
Definitely. So before we get into the experiment itself, let's just quickly set the scene. Why does the Amazon matter so much? What kind of scale are we talking about?
Oh, the scale is just immense. Think about an area roughly twice the size of India.
Wow.
Yeah, stretching across Brazil, Peru, Colombia, several nations. It's the world's biggest tropical rainforest, by far.
And its role in, the climate system, carbon storage.
Hugely important. The reporting points to estimates suggesting it holds carbon dioxide equivalent to about 2 years of all global emissions.
2 years worth. Locked up in the forest.
Locked up in the trees, the soils, the whole system. Which brings us to the risk, of course.
Which is if those trees die.
Exactly. Whether it's logging or, crucially here, drought stress. When the trees die, that stored carbon goes back into the atmosphere. It speeds up global warming. It's a feedback loop.
And this isn't just theoretical. We're seeing signs already, aren't we? The Independent piece mentioned recent real-world droughts.
Absolutely. Driven by El Nino, by climate change, we've seen devastating impacts. Mass deaths of river dolphins because the rivers got too warm and low.
Horrifying.
And wildfires, even in parts of the rainforest that usually don't burn. So the threat is very real right now.
Which makes this experiment, Essekaflor, even more relevant. Scientists basically decided, let's not wait for the worst droughts, let's create one.
Kind of, yeah. The Essekaflor project, that stands for Forest Drought Study Project, kicked off way back in 2000. Brazilian and British scientists working together in the Caxiuana National Forest.
And how do they actually do it? How do you make a drought in the rainforest?
Well, it was quite an engineering feat. They took a plot about the size of a soccer field, so 1 hectare or 2.5 acres.
Okay.
And then they built this huge roof structure over it. Thousands of clear plastic panels.
A roof made of plastic over the trees.
Yeah, but set quite high, a meter high at the edges, rising to maybe 4 meters in the middle so it didn't crush the vegetation, and angled.
Angled why?
To catch the rain. The whole point was to intercept about half the rainfall that would normally hit that patch of forest. The panels funneled the water into gutters, then into trenches dug around the plot, leading it away.
So they effectively put that whole hectare on a 50% rain diet, permanently.
Pretty much, yeah, for over 2 decades. And crucially, right next door, they had an identical plot. Same size, same forest type.
The control plot.
Exactly, untouched, getting all the normal rain. So they could directly compare what the lack of water was doing separate from any other changes.
And then they just watched. What do they measure?
Oh, they measured everything imaginable. Instruments on the trees, on the ground, buried in the soil.
Like what specifically?
Well, basic stuff like soil moisture, air temperature, humidity, but also how fast the trees were growing, their girth, how much water was flowing up the stems. That's called sap flow. They looked at root growth underground, how the leaves were functioning, the plant physiology, really detailed stuff.
And the report mentioned NASA. How do they fit in?
Yeah, that's pretty cool. They have these metal towers over both plots, the drought one and the control. And NASA radars on those towers actually measure the amount of water inside the plants, in the canopy.
Seriously? They can measure the water in the leaves from a tower?
Apparently so. It gives them a sense of the overall hydration level, the stress. That data gets sent off to NASA's Jet Propulsion Lab. It just shows the level of tech involved here.
Incredible. Okay, so this massive, long-running setup, decades of data. What did they find? What happened to the forest under this simulated drought?
Well, this is where it gets really interesting. According to Professor Lucy Rowland, involved in the project, the first thing they noticed was Surprising resilience?
Resilience, yeah.
For about the first 8 years or so, the drought plot didn't seem drastically different from the control plot. It was, coping.
8 years holding on with half the rain.
Right.
That's quite something.
It really is. But the key finding, and this was detailed in a study just this May in Nature Ecology and Evolution, is that there was a tipping point. After those initial 8 years, the cumulative stress really started to show. They saw what Roland called a really big decline in biomass.
Meaning trees started dying.
Yes, significant losses, especially the biggest trees, the giants of the forest, which, crucially, store the most carbon. They were hit hardest.
So the resilience had a limit. And losing the big trees, that must have impacted the carbon storage dramatically.
Hugely. They calculated that the drought plot lost about 40% of its total vegetation weight.
40%.
40%. And with that, 40% of the carbon it had stored, gone, released.
Wow. That's a massive change. More than just ecological damage, that's a climate feedback right there.
Absolutely. And it led to this critical shift. The paper explains that during those years when the trees were dying off most rapidly, that section of forest actually switched roles.
Switched roles.
It went from being a carbon sink, absorbing CO2 from the atmosphere, to becoming a carbon source, an emitter. It was releasing more carbon than it was taking in.
So the drought literally turned that piece of the Amazon from part of the solution into part of the problem, at least for a time.
Exactly. Now, the study mentions it did eventually stabilize at a new, lower biomass level. But that period of being an emitter was a really stark finding.
Very stark. Now, the reporting also mentioned something, maybe slightly less alarming, something about savannas.
Ah, right. This is an important nuance. Some earlier climate models had predicted that severe, prolonged drought could actually tip parts of the Amazon over into becoming a savanna, a much drier, grassier ecosystem.
Like a fundamental transformation.
Yes. But in this experiment, even with the 50% rainfall reduction for over 20 years, that didn't happen. The forest structure changed massively, huge tree loss, yes, but it didn't flip into a savanna.
Okay, so not a savanna, but still, a forest that lost nearly half its weight and temporarily became a carbon source. That's still pretty worrying. What's next for the experiment now?
Well, they entered a new phase just last November. They actually took down most of those thousands of plastic panels.
Really? So the artificial drought is over?
For most of the plot, yes. The focus now shifts entirely to recovery.
Recovery. Seeing if it bounces back.
Exactly. Joan Deathaides, one of the coordinators, explained it well. The forest clearly adapted to the stress by shedding biomass, changing its structure. Now the question is, can it regenerate? How quickly? Can it get back anywhere near its original state?
And they're just going to keep watching.
That's the plan. The project doesn't have an end date. It's a long-term commitment to understanding not just the decline, but the potential for recovery, too.
And the report mentioned a recent site visit. It sounds incredibly remote.
Oh, definitely. To get there, it's a full day's boat trip from Belém, which is interesting because Belém is actually hosting the big UN climate talks soon.
Huh, fitting.
Yeah. And the researchers stay out there at a dedicated scientific base. During that visit in April, the report said there were 4 different research teams all working there at once.
4 teams? Doing what?
All sorts. One team was digging soil pits, looking at roots. Another was monitoring weather, soil temperature, moisture. A third was measuring that sap flow again, water in the plants. And the fourth was focused on plant physiology, how the plants are actually functioning at a biological level.
It just shows how many different angles you need to study this.
Absolutely. And even after all this time, there are still big questions. An ecologist, Rachel Selman, pointed out they still know relatively little about how the drought affects all the processes happening in the soil. Below ground is still a bit of a mystery.
Right. So let's pull this all together. 24 years, this incredible effort. What are the key takeaways for us, for the listener?
I think the first is undeniable proof. The Amazon is vulnerable to long-term drought. That initial resilience, it was real, but it has limits.
And hitting those limits means serious consequences, major carbon loss.
Yes, and that critical shift to becoming a carbon emitter, even if temporary, that's a huge warning sign for the wider Amazon under increasing climate stress.
But as you said, it didn't become a savanna. There's this more complex picture, emerging severe impact, yes, but maybe not total collapse. And now this question mark over recovery.
Exactly. It's not a simple story. It provides crucial, real-world context for the droughts we're already seeing, and it hammers home that what happens in the Amazon doesn't stay in the Amazon. Its carbon balance affects all of us.
So for anyone trying to understand climate change, ecosystem tipping points, maybe for exams or just to be informed. This experiment is fundamental. It's observed reality, not just a model.
It really shows the complexity, vulnerability alongside potential resilience. It's messy, like nature often is.
So wrapping up this deep dive then, this incredible multi-decade experiment shows us an Amazon vulnerable to drought, capable of losing huge amounts of carbon and becoming an emitter.
But also, perhaps, having ways to adapt or recover that we didn't fully anticipate, even if it doesn't prevent major damage.
Which leaves us with a really profound final thought, doesn't it? Given this complex picture, the massive carbon loss, but no savanna shift, and now this focus on recovery, what does this mix of fragility and potential adaptation actually mean for the Amazon's future in a climate that's only getting hotter and probably drier in places?
That's the multi-billion-dollar question, really. It underscores why we need both climate action and continued research like this. Urgently.
Absolutely. Well, thank you for joining us on this deep dive into the Escaflor experiment.
And remember, our discussion today was based on that excellent reporting from The Independent.
If you found this useful, maybe clarifying some complex issues, or if it sparked your interest, especially if you're tracking environmental current affairs, please do give us a like or subscribe for more deep dives.
And please leave a comment below any questions you still have or your own thoughts on what this means for the Amazon and for us all. We'd love to hear from you.